First question is let's go back to why are we learning programming language? We would like to know about the mechanism for programming language, right? And then in the old days, like 20 years, 30 years ago, we actually focus on developing the microprocessor, right? Microprocessor and then compiler. And then inventing new kind of the machine. Say we have a PC, then we move on to to our cell phone, right? Something like that. And then we start to have the browser and then app, right? So in the old days, actually, programming language is more like developing the compiler on the machine. But nowadays, the chance to develop a compiler is very less, right? Very few chances that we would design a compiler from scratch. So why are we learning this programming? The knowledge that we learn, where can we use it for taking this course? Where can we use the knowledge for programming language? Sunny, do you have an idea?
You can use it to develop like applications for mobile.
Yeah. What type of application?
I guess like maybe financial applications.
Oh, okay, that's good. Yeah, that's good. But actually, that's actually a good answer. Let me be more specific. Okay. So let me show you one thing. Okay. Let me show you one thing. Okay, compiler is the old day terminology. Right here, let me actually bring up this. This is called what? Google, right? And the software I'm using is Chrome, right? So right here, I actually do about blank, right? What's this for? You click right click and inspect, right? And you bring up this. What's this?
That would be like, I guess like the web page itself, like the blank space.
Yeah, so this is a blank stage, right? Right now it's blank page. So here, if I right here, I have a console. I move to console, right? And then I say document dot write, right? And here I say like hello world, right? And then let me do this plus bracket br, right? And this hit enter. Okay, go to there, right? And then actually I can hit element, right? So when I hit element, it talk about the HTML text, right? And this is the bounding box, right? And this is your document, right? Your HTML page, dynamic HTML page. Here I have a console, right? Here is I have a console. So let me repeat one more time. You starting from here, we have about comma and then break, right? We bring out a empty page, right? And not empty page it's like a canvas or some sort of a page that you can see, and you hit return and you select console. So here I can do like variable a equals 3 and variable b equals 4, right? And then I say document dot write, and here I put a plus b, right? It will be 7. It will be 7. And then what's this? What's the console we see here? How do you call this guy? I mean the console. It can process the JavaScript here, right? And it print out something here. And how do you name this guy? Do you know what my question?
I'm not sure.
Okay, let me see. Hello, hi Jiang, how are you? Hello? Hear me? Okay, my answer to this is that this actually is an interpreter. So it's like you bring up the Python. You bring up the Python, say if here I have a page, right here I bring up the Python, right? And then here I do Python. No, this I don't have Python here. Let me see. Oh, I've misspelled. Okay. I bring up Python, right? And Python is an interpreter. So I say A equals 3, right? And then B equals 4. Let me see. Okay, A equals 3, B equals 4, and then I print now A plus B, right? So it's the same. So Python is an interpreter, and then my JavaScript is also an interpreter. So basically, here we have a web engine. We have a web engine on our browser. So our browser called Chrome, right? Our browser called Chrome. But inside Chrome, we have a web engine. Web engine will interpret your HTML, CSS, and also JavaScript, right? And then you have a JavaScript engine. And that actually is an interpreter, right? So browser has an interpreter built in there, and it will interpret whatever command you have, right? So instead of writing the full-blown compiler on desktop, actually nowadays a lot of application, it actually can be processing your HTML or whatever code you rewrite in HTML, JavaScript, like an app or something. It will have this so-called engine, the JavaScript engine in there. So that actually is handled by this different engine there. So this actually is what? It's a script-based environment. It's okay. So basically we learned the first two chapters in order to know about how compiler is being constructed. And also it's not there only. We actually can bring up for each different app, different browser, and different app, different browser, and different devices. So you have a central server, right? You have a server, and this server may have associated with hard disk, right? And you have a computer, you have cell phone, you have a pad, right? And each one of them can actually browse it. And each one of them is called a viewport, right? It's a viewport. So the data being transmitted back to here, if you have an HTML request, the data being transmitted back to your computer, right? And it shows on your computer or pad or cell phone. And each one of them is a viewport. But each one may have an app and may have a browser. And on the browser or app, there is a JavaScript engine, and there is some sort of web engine over there. Is that okay? So interpreter now is hiding over here. Interpreter now is hiding over here. Okay? So we learned this different kind of the context-free grammar, regular expression in order to search web searching. In order to do web searching. And now people call it information retrieval. Okay, this is called information retrieval. And you do query. You do all kinds of queries. So you may have heard the word Q query. And the query being made by JavaScript actually try to help you to identify the data. So we specify the regular expression, context-free grammar, all kinds of different things to search data. So you can actually do search engine, right? And then do information retrieval. Okay, you do this, right? There's some book you can you will see there's some book doing the search engine information retrieval, and inside there inside this book you will find something like text processing, regular expression, processing text, tokenization, then streaming, link analysis, right? This different thing actually is originally query expansion. This different thing originally being developed in compiler. Now it's moved on to the engine in your search engine and then in your web browsing things. Is that okay? So this field is not dead yet. In fact, it actually moved on to information retrieval on your browser. And what we are doing right here actually is not only supporting the computer, but also give you the idea of the structure for search engine, text processing, crawling, fitting, right? And then you do conversion, processing tags, tokenization, right? Tokenization is one of the things you do using the regular expression, right? Coding things, okay, whatever. So later I'm going to send this link to you anyway. So we actually not only developing the compiler. This knowledge is not limited to compiler, but it actually can support whatever web browsing you have, the queries that you made. Okay, and now people are moving to this so-called scripting language. So Java 8 is still a desktop language, but now we have Java 9, 10, 11, and Java 11 Java 9 start to pick up the module programming, and then Java 10 start to have a local variable for actually a type independent local variable var type variable in Java. They don't have that, and it is supported now. So Java actually is moving toward the scripting language side, okay? And also there is a Java shell, right? Java shell. So Java shell actually also is an indication that Java is moving to the scripting language side, okay? So here we actually talking about this different language and also talk about the language application. And we finished that different state machine stuff. And this chapter we start to talk about the data type, data's lifetime. And this different data type highly depend on the memory model. Okay, some term I'm going to use called memory model. And each memory model on desktop, you are C language, there's a C language data model. And on the scripting language, you would have the object model, object management model for, say, JavaScript object model, okay, DOM model, right? These are something we do on our browser side. So in order to master a language and also the language model, you have to know about what memory model has been used. So this chapter actually dedicated to the memory model, including the name of a variable, scope of a variable, and also binding of the variables. Okay, so let's get started. So overview of the name, scope, and binding. Name, scope, and binding. A name is exactly what you think it is. It's the name. And sometimes in the programming language, you call it ID, right? It's identifiers, and there are some rule about ID. You cannot have the number to lead the name of the ID, and you need to have underscore or maybe $sign in some language to start an ID or a capital letter or a lowercase letter, right? That's a name. So every variable have a name. And then every variable has a name, right? There's a name about a variable, and there's some value can be put into there, right? So this value and name, there is an association between the memory and your name. These two, the association is called a binding. Okay, the association is called binding. The name is the ID you have, say X, right? You have an integer X. That's the name, and this is type. And then name associated with the memory, say the memory address F3 2A, then that is the address, right? So you have the name and address association that's called binding. And the lifetime that the binding exists is called the scope. Okay, the lifetime of the binding is called scope. So we have the local variable, we have global variable, we have static variable, we have instance variable, right? We have dynamic allocation memories. So these are different terms for binding, and we will explain these different terms. So that's actually is the memory model we talk about for the variable environment. So all of the environment that combine everything, name, a scope, and then binding everything in a programming environment is called a reference environment. The whole thing is called a reference environment. Okay, so we have name, binding, scope, and now the whole setup is called a reference environment. So let's go. Okay, so name. There's a name called John Smith. Maybe an office person, maybe a baseball people playing kid, maybe a soldier, maybe a cosplay player, right? And actually, it can be by a different person at different times. Say we watch a person, kids playing basketball, and this binding, the name would be by with this kid, right? And that actually depends on when are we talking about this person, John Smith. It can indicate different person, okay? So name, scope, and binding, we have different type of variables. So we have static variable and instance variable. So static variable is what? It's a variable that actually when the system exists, your programming a program exists, it start to exist, and it never change the memory location. The binding never change. That we call static. So in Java, we have static variable. It will be put into the method area, the intern string, and global memory. It will be on the non-heap memory, and we call it global area. Okay. An instance variable, we create an object, and that object will be put into heap. Okay, put into heap, and then we will have that actually these two can be considered as global variable. Either is in the non-heap area or heap area, but heap area usually is a shorter time because your instance can only exist when you actually create an object. If you haven't created an object, it is not existing, right? But static variable usually you put into the C language's global variable area, or you put into the static variable of a class in Java. That actually would exist when program start. It will be existing. Okay, then we call it static variable. But some instance variable it will only be available when you create an object. Okay, those are global variable. And global variable means like as long as the object is created, okay, you do whatever function call, it doesn't matter. The object still be there, the memory still be there, it never changes. Those kind of variable, we call it global variable. Independent of the function call, we call it global variable. And local variable means what? Means it actually depends on where you are, your program counter, where your program counter is. So you may have block level variable, you may have loop level variable, you may have function level variable, you may have parameter list variable, you may have module level, package level, or even some variable defined in namespace. Okay, so those variables will exist when the function is called or if the code block is called in the code stack. Okay, in the code stack. And if that stack frame being pop up, then the variable won't be existing. Is that okay so far?
So far, so good.
Okay. If you have question, let me know. Okay, so then we have the name, scope, and binding. Okay, right here. Right here, this one actually is like, I have a main program, and this main program is pretty simple. Let's assume that this main program is a Java program, and we have a main function, right? And inside this main function, I run a student s equals new student, right? And then to the age 23, name is John, okay? So I could run this constructor once, right? And the constructor, inside the constructor student, actually I'll call the function called setName. Okay, and sudden has a string over there. Okay, so basically main function call constructor, constructor call setName. So at the main function level, I have a student class, a student, a reference. The name is S, and this S is pointing to a student object. As long as the object is created by the new student function with 23 and there's John as a string. Because John is a string, so it actually is another reference variable that pointing to a string that's stored in heap called John. Okay, so in my call frame of the main function, you have the student variable S and a value that's the number of students. Okay, the number of students is a primitive data type, so it actually is a value stored in stack. And S is a object reference, so actually it stores the ages or H code of the object, student object, age 23 and reference John. Okay, so this is the main function. So there is a reference variable S. And then you call the student constructor. So basically you pass two variables into there, you have the age and name being passed to there, right? So age is used to set the age in the student object, okay? And in this call frame of the student constructor, you have a implicit pointer, implicit reference variable called this. In Java language, they said this reference variable, and that this reference variable usually pointing to the current object we talk about. So it actually is also pointing to the student object with an age and name, age 23, name John. Okay, so this is the implicit object, and then the parameter has the age and name, and age is stored with 23, and 23 have been used to construct the object student 23 and John. Okay, and then you in your constructor you call set name, and set name has a name variable that's pointed to John, and the implicit object reference list still exists, is still pointing to the student object. Okay, so this is actually the binding of your a Java program, simple Java program that has main function calling constructor student constructor, and then call the function setName. Okay. So binding time is the time in which the binding is created. Okay, that's called binding time. And binding is the lifetime is the association of the memory and the name, or more generally, the point at which any implementation decision is made. It can be design time, it can be language implementation time, it can be of different time. Let me see. Okay, I'm sorry. So the binding can be done actually language design time, language implementation time. So language design time actually is that when you have some variable name like null, or it's some variable name like undefined, those variables are defined in the language design time. Okay. At the language implementation time, you can also have, those variables like undefined or not a number, those kind of variables still can be designed when you do a language implementation. That actually depends. Okay, depends on which language you talk about. Let's go back to our this one, our JavaScript engine. So here you may have like you can do variable a equals undefined. That is okay. Okay, so a it is undefined. Okay, and you can do a equals null. Okay, these are the variables that actually been defined at the so-called language design time, or the implementation time. It actually depends on the language. Okay, and also depends on the implementation of the language. But these are not the common variable we know. These are the rare variable. Only a few, for each language, there are only a few variable would have such feature. Normal variable, it will have the binding at what? Static time or dynamic time. Static binding means that the binding is done when we do compilation. So compiler determine where the memory associated with a variable. That's called static binding. And late binding or dynamic binding is like the name and the memory address is usually is determined at the running time. So basically, when you have something like a new operator in C++ or Java, new say a object and then assigned to something, this is actually the dynamic binding. Okay, and if you compile using integer a equals 3, this variable binding with the memory will be done in compile time most of the time. That's called static binding. Okay, so that's the difference between static binding and dynamic binding. So, and we also have different binding. These are also runtime or dynamic binding, but we still have parametric binding or polymorphic method binding. Okay, so parametric binding means that when I call a subroutine and I pass the parameter in, that parameter bind with the data with the parameter. The formal variable bind with the actual parameter. That's parametric binding. So it actually assigns some value from an actual parameter to the formal parameter. Okay, and when you get out of the function or subroutine, you restore the original value of the A, B, C. Then the whatever local variable or parameter will be unbind. When you return. Okay, that's called parametric binding. The other same on the right side is called polymorphic method binding. It is the dynamic binding for Java. Okay, so polymorphic method binding actually is you have different definitions. Say here we have an object called class. I'm sorry, object called color. Okay, so I'm sorry. This actually is an object. Okay, and you have different class, a subclass called point and color the point. Okay, so point class inherit object class, and color the point class inherit point class. Okay, and each of the class is a template, so you can use that to create object. Okay, so here this one like someone like orange color is an object. Blue color are the classes. Okay, so there's a virtual, there's a VMT that will be available. It should be a virtual memory link or something. Okay, so we create different objects, right? And they ask different methods. So if we actually say create a color the point, okay, and actually this color point is a reference P point that actually pointing to color point, right? And you set the value of the 10, 20, and color red into the P. So this P actually is an object and is of color point type object, okay? And P is a reference variable. So we do P that get color, and get color because it's defined in color the point class. So you will access the copy of the get color at the color point class. So basically this get color is bind to the function that defined in color point class. But if you run p.getX, there is no definition in your color point class. So you will get the copy of the getX and getY from the parent class point class definition. And this we call it is a dynamic binding, and also it actually is polymorphic method binding. So the basic rule is that when you call a function, you will try to find the definition of the function in your own class. But if your own class does not have the definition for the function, then you have to search for your parent class to get the definition. If not, then you go up to your grandparents' class. If not, you go up until you reach the object class. If there is no definition for that function, then it will complain about there is no matching function in that class, in that object. Is that okay so far?
Yes.
This is called dynamic binding, or sometimes we call it polymorphic method binding. So binding actually is association of your function with a function name, or association of the memory location with a variable. Both of these, binding a data field or binding a method, are called binding. Okay, and there are several levels of binding available, and it actually depends on the language as well. So parametric binding, when we do generic programming, we have a generic class called generic box. And there is a type variable. When we declare in Java, there's a type variable, and that type variable T is available, but it only can pass something like integer object class over there. Or you can put a double, or you can put a string to that, and then that type is matched with another type. So usually it's a reference type. And then generic binding, we have generic class, container, generic function, and generic iterator, 3 types of generic programming. Okay, and that's parametric binding. In C++, we have namespace binding. So a function will call a variable that define with a certain namespace, say statistic module. And that statistic module will depend on the import function. And import would actually call the base namespace. And base namespace go to global environment, and global environment check the state package, something like that. So then C++ namespace binding will have different level, and you have to check the level to find out where the function actually will be physically binding to. Okay, so C++ use different way for doing dynamic binding. We call it virtual function. Okay, we call it virtual function, and virtual function is somewhat like the dynamic binding in Java, but it is a little bit different because it uses a virtual pointer and virtual table to achieve it. Okay, so you actually have a base class, and then you have 2 derived class. So derived one actually inherits a B1. Okay, and then that object can reference to a table called vtable. So VPTR is a virtual pointer which point to the virtual function for that object. Virtual table is a table containing the ages of virtual function of each class. Okay, so here C++ has dynamic binding, and the implementation of the virtual function in the dynamic binding for C++ language is through the virtual function. A virtual function look up its implementation defined in the vtable. Okay. Any question?
No questions so far.
Okay, so far we talk about the binding. Okay, so binding is determination of the memory and its associated name. Okay, and it can affect variable, and it can affect the functions. Okay, now that's binding. So now let's talk about the concept of the binding time. Okay, binding time, as I mentioned before, it has language design time binding, it had language implementation binding, it had a program writing time binding, it had compile time binding, and it has link time binding. This actually usually called static binding. And then you have load time binding, like who is load time binding? Java's static variable is load time binding. Okay, and then there is a runtime binding that actually is Java's function. Okay, this actually all depends on what language. Not all languages support all of different binding time. Okay, so it really depends on the language. But here is a summary of all kinds of binding for all languages. Okay. So here we have 4 different language. Each one represent one type of binding. So let's look at the C++ and Ada. Okay, this one is a traditional compile, link, and go process. Compile, link, and go. Compile means that you have source code. Your source code being converted by compiler to object code. So that's .o code or .s code. And then that object code being linked with some library. So that's link time. So first time compile, second link, the third stage, you have the .exe file, then you go and run it. So this is compiling Go. This one actually, since 1970, C language come out, we have been using this compiling Go process, okay? And then we have, next one is the Java style. Java style have compile, load, right? Compile, you compile it to bytecode. The bytecode being loaded and then interpreted by the interpreter, the Java virtual machine, and then link, dynamic linking, right? And then just-in-time compiler and go. So it's a compile, load, interpreted, link, and compile and go. The process a little bit more complicated because it has a virtual machine. Okay, but it actually somewhat still follow the compiling Go process that actually defined in C++. And we may have other language like C#, .NET environment. It actually is the dual pass compiling and say just-in-time compiler and go. So it has the dual pass. That means that you have compiling Go feature and also compile link and compile load, interpret link, and just-in-time compiler and go. Okay, so on the right hand side we have virtual C++. We compile and then link and compile. So this actually has the dynamic linking. Okay, on the left hand side we have Visual C# project. We have C# source file, and we have the resource locator, and then they put things together to C# compiler, and it becomes the managed assembly code. So that is somewhat like a bytecode, and then you load the C# assembly code into the .NET framework, and .NET framework just like Java virtual machine to run it. And at that time, it's just like a just-in-time compiler and then run it, okay? So C# and Java are similar. It has the compile to bytecode format and then load the bytecode and interpret and go, okay? On the left-hand side, we have compiling Go for the JavaScript. This one actually is somewhat different. You write your JavaScript, right? And then you actually load your HTML and your JavaScript into memory, and it actually create the DOM first, create the HTML document object model first, and then with that object document object model, we load the JavaScript in. So at that time we do compilation, and then we have the JavaScript function, and then we link it and then run it. Okay, so it's a compile and then link and run process, but actually it all happened on the web engine and JavaScript engine. So implementation decision, at runtime we can determine a value, variable, binding, size of the string, array, static heap, and stack. And we subsume the program start time, there's load time, module entry time that's used, elaborating time, a point which that the declaration is first thing. So elaboration is the definition of the variable time. Procedure entry time is call time. Block entry time is called run over time. A statement execution time is called execution time. So basically, the runtime still have many different timing. Okay. Namespace and binding. The terms static and dynamic are generally used to refer to things bound before runtime and at runtime respectively. So basically, usually static is a constant. It usually means the compile time, and dynamic is usually mean the runtime. But these two terms have to be carefully used because sometimes they actually mean different things. Okay, in general, early binding time are associated with greater efficiency. So if you use the static binding using compiler to bind it, it actually is more efficient, but not as much flexibility. Okay, that means that if you have the dynamic binding, usually because it's not linked, the program is not linked yet, so you can ship the program to different implementation or installation environment, and the programs can still be run. And if you actually not using the late binding, you use the early binding using compile time binding. Usually the execution code had already been determined, so you cannot rebind the data to different location, or you cannot bind the function of different implementation. So that actually is not expressible. So interpreted the language tend to have late binding because it's script type. So usually it depends on the environment. And the compile language usually is more early binding, and it actually has less flexibility, but usually has better efficiency. Scope rule, control binding. Fundamental to all programming language is the ability to name data or refer to the data using symbolic identifier rather than ages. So here we have something called ages and symbolic identifier, right? And actually in C double plus language, we have something called alias. Okay, you can have, say, student alias type, right? You have an alias type, and this alias type create a different alias for a variable, right? And actually can use that alias as good as the original student reference variable S. Okay, these two actually pointing to the same object. Okay, that's how actually the symbolic identifier can be used. So actually, this also depends on the language. Okay, polymorphism. Polymorphism, here we have 4 types of polymorphism. We have ad hoc polymorphism. We have universal polymorphism. The ad hoc polymorphism actually use that when actually at design time we do the assignment. Okay, it actually is overloading, overriding polymorphism, and we actually overload some function or override some function. We call it ad hoc polymorphism. And the other type is coercion. Coercion polymorphism means you cast one variable to the other. So we originally may have a variable, double typed variable D, and we actually assign it to integer x equals int double D, and that actually, this operation is called a coerced polymorphism. So we can convert the type of the variable to any other type, create polymorphism. But usually this is called ad hoc polymorphism. And we also have the inclusion polymorphism and parametric polymorphism. Inclusion polymorphism actually means the inheritance structures of polymorphism. Say we can use object reference A equals new student, and student is an object type, right? But the reference is assigned to a superclass object's reference type A. This is called inclusion polymorphism. So sometimes we call a for each loop, we can do for each student, okay, A, and then we can have some student, or we can put object here, right, from the object list. But each of the object can be of student type, of person type, of different type. But when you do a.print, you print out a object, but in different format. We call this inclusion polymorphism. And parametric polymorphism means the one we talked about before. It has 3 types of polymorphism created by parametric polymorphism, including the parametric function, parametric container, and the parametric iterator. So those are using the type variable T or type variable E. So you can assign the different type to the type variable to create parametric polymorphism. Is that okay so far?
That is fine so far.
Okay. And this different type of polymorphism, you have a static binding and dynamic binding, okay? Yeah, this portion actually is a little bit more abstract, okay? Okay, we finished binding time, right? Binding time talk about when we will bind it. Now the next one is the lifetime. So lifetime is the scope. And scope, as I said, is the existing time of the binding relationship. It's called scope. So lifetime and storage management, key event in memory management, creation and destruction of the object, creation, destruction of binding, the activation and reactivation of binding that may temporarily be unavailable, reference to available subroutine type, and so on, all of which use bindings. So basically, lifetime and storage management are talking about binding may appear, may disappear. Okay, it depends on what type of available you have, right? Global binding, global available, the binding is always there. Local available usually have to depend on your co-frame. Your co-frame, you have a frame, you put a few variable in there, right? Your A may be here, but if you have a subroutine and it also have variable A, the definition of these two variables are different. Okay, so that actually is the lifetime or the scope of the variable. And it depends on the language as well. So the period of time from creation to destruction of a binding is called a lifetime of a binding. If an object outlives the binding, it's garbage. What's that? If a object outlives, so you create an object, you assign that to a reference variable S, right? And actually somehow this S linking is dropped. Nobody pointing to it there. And this object becomes garbage. Okay. And you actually have a pointer and associate with the object, but the object being deleted. Then we call it a dangling reference. This S is a dangling reference. Okay. So object and reference, sometimes they are not existing at the same time. Then it may be a garbage or it may be a dangling reference, depending on who got deleted first. Okay. The textual region of a program in which the binding is active is called its scope. So scope means the binding is alive. Scope means the time that the binding is alive. In addition to talking about the scope of the binding, we sometimes use the word scope as a noun all by itself without an indirect object. Okay, so this one is a simple sample class. So here we have a charge class, right? So this charge is, we talk about physics, okay? We talk about physics. So we have what? Our force equals K times Q1, Q2 divided by R squared, right? So Q1 is a charge, Q2 is another charge, right? So there's some force, either impulsive force or attractive force. Okay, no matter what. So we have a charge, it has a quantity in coulomb, right? In coulomb. And then we have the relative H's, I's, and Ry. So that define the charge location and charge quantity. And then we have the constructor that create charge, right? And then we have function to string to print out the charge. And we have the main function to test the charge. Okay? So in our main function, we create a double parse, and provide some argument, and we create a double variable to X, and then we create Y, right? And then we create object C. So when we create object C, the C type, it actually is reference data, and the object will put into heap. Okay, but the reference actually will be put into the step because it's inside the main function. Okay, so whatever put into heap will be the objects. Okay, whatever put into the master area will be the class object. class variables. So that class variable will including the methods and the static methods and the constants and the static variables. Okay, and local variable will be put into the stack when it is called, and then instance objects will be put into the heap area. Okay, lifetime and storage management. So we have different mechanisms. We have static type, heap type, and then there are different operations to be done. Code, global, static is all on available, and it presets the constants and the scalar to be stored in the instruction. So here I don't go into the detail for this, and it has different definition, and that's the memory model for Java for this one. Okay, so lifetime and the storage management. Central stack. The stack will be used to store the parameter, local variable, and temporary variables. And why we use stack? Because stack allocates space for recursive routines, and also reuse space if some object being destroyed or being garbage collected, then the area can be recycled to be used. So it is somewhat more efficient if you have a garbage collection. Okay, here we have the function calls. So the pseudocode is on the right hand side. We have a main function that run A, and procedure A run B. Procedure B will run if some condition you run B, then run C. And then C procedure will run D and E. So basically, here A function call B function, B function call again the second B function. Okay, and then it call the C function, and C function will have a call frame like this. Okay, and then C call a D function. Okay, so basically that's how stack-based the location of memory being shown. And in here we have the so-called call frame, and each call frame has a memory address pointer. We call it frame pointer. Okay, and frame pointer pointing to current frame. And in the current frame, you have the return address, local variable, and argument to the routine. So usually this is called a call frame, the temporary variable, local variable, and arguments and return address. And these are prepared to form the environment of a function. So the local variable will be defined over here, and when you refer to some variable, it will check this call frame first. If some variable is not found, then you go to your global variable, global area to find global variable, or it will complain, or it may be creating some compile failure. Okay. So stack and the call frame. Maintenance of stack is responsibility of calling sequence and subroutine, and we call it prologue or epilogue. Prologue is run before entering the function. Epilogue is the exit procedure for quitting the function. Okay, space is saved by putting as much in the prologue and the epilogue as possible. Okay, time may be saved by putting more in the body of the subroutine. Okay, and putting stuff in the caller is instead, and combine what's known in both places. Okay, so here are the epilogue and prologue. There's something you need to do before you transfer the control to a different function. Okay, and heap is for dynamic allocation. So usually use the constructor, this constructor, to manage your memory dynamically. So you may see the memory allocation function, C allocation function, or free function in your C double plus or C language. And garbage collection. Garbage collection actually, as I said, garbage is defined as the object that has no one to refer to. Okay, and then if no one refer to, then it will be considered as garbage. And we will have mark and sweep algorithm. That means that from time to time, our garbage collector will search for our memory to mark those unused block and then clean them out. Okay, so that's called mark and sweep algorithm. Okay, so it actually mark and sweep algorithm. We will officially talk about it in more detail in chapter 8. Okay, so it basically going through the whole memory, checking for every object. If it is unreferenced, then we mark it. And after that, we actually clean this mark area. And that's called recycle of the memory. And then you may use some algorithm to do the fragmentation to make it the memory more compact. Okay, that's another issue that actually has nothing to do with garbage collection. It actually is the optimization of the program. Okay, but mark and sweep algorithm is used to clean out the memory for the garbage. Now the next one is the memory model. Let me see how many slides we still have. So here we have in 33 about 1/3 of the chapter. Okay. The next one is memory model. So here we have the C memory model. And as I said, C language is used for manual machine. So all manual machine is based on C language model. So whatever desktop programming you have done on personal computer, it may be Java machine, it may be a Python version machine. It all been designed by the C language. So when it runs, it actually following this C language model. Okay, and the whatever Java memory model or whatever Python memory model, actually you are talking with a virtual machine. So it's another layer of abstraction. So the lowest level is usually C plus memory model. We call it memory native function or native methods. And you would have an instruction area, instruction segment, and then data segment, and then extra segment, and then stack segment. So basically, a process image, we call this process image, in your program would have data section, instruction section, segmentation section, and extra section. Okay, you may learn this term from the operation system course, but basically for programming language, we deal with these for different segmentation. Okay, this is .NET model. The .NET model is similar to Java model. So right here, I just briefly mentioned about it has the managed core and unmanaged core. Okay, so it's a little bit too much. And Java virtual machine, we have the runtime data area. You have method area that's actually used to store constants, method code, and also the static variables. Okay, and you can also have a heap. Heap is used to store instance, array, and strings. Okay, and then there is a per thread stack, per thread red purpose program counters. That's Java's memory model. And this one is the JavaScript memory model. So we have browser engine. So when you bring up a page, the browser engine will build a DOM first, document object model first. You have a window document form and other node. Okay, and then you load your JavaScript, and JavaScript has its separate object space and JavaScript engine. That's what I say. In here, when we actually run our page, it is running this JavaScript engine. So JavaScript engine somewhat is like an interpreter, and it manages memory by itself. It manages memory is by itself. It has stack. It also has the object space, and the object space and the browser object space DOM actually will be the objects that can be operated by JavaScript. And here we have Python memory model, and Python is also similar to Java virtual machine. It has a Python interpreter, or we call it Python virtual machine. So lower than certain level, lower than the Python raw memory allocator, it actually is the same as the C language. So lower level for Python actually running the native code. Those are C language. And upper level, we actually have the heap and the Python object allocator. These are actually written in C language, but it performs like it's pure object environment. So all the C or machine-related issues have been hid by this Python memory model. Okay, then we'll start to have a few section 1, 2, 3, 4 for the scope rules, and then we will have the name within scope. Okay, and then we are going to binding reference environment. So we basically finish the basic definition for name, scope, and binding. When we talk about binding, we finish the binding and storage level, and we finish the memory model. Now we are entering into scope rules, and also we'll talk about the reference environment as well. Okay, that's what we will do. But here, because some of the rule is very much detail, so if it is not very essential, I will just omit it. Okay. So first one is a scope rule. So scope, as we say, is the lifetime of a binding. And in most language with subroutine, we open new scope on subroutine entry. So every time we call a function, it has a new scope, and we can create a local variable on it. So we create a new scope because actually it is a different level of the call frame. When you do the call stack, it is a certain call frame over there, so it's a new scope. And for scoping, you have the static scope and dynamic scope. Okay, so static scope means like at the compile time we know about it. Those language will be like C, Java. Those are static scope. And actually, Python or Lisp used to be dynamic scoping, but actually a lot of dynamic scoping language already keep up, because it's so difficult to track the function's behavior. Okay, so dynamic scope right now, I believe not a lot of language actually implemented. So the mainstream would be static scoping. So the scoping is determined by the function level, or it will determine at the compile time. It's called static binding. Okay, so scope rules on subroutine as a destroy binding for all local variable. We activate binding for global variable. Okay, and this we have Argo 68 elaboration process of creating binding when it enter the scope. So this older language, I tend to not to talk about it because not a lot of people using it now. And scope rule, the next word is reference environment. Is the set of active binding that we call it current reference environment. So it's the set primarily determined by static or dynamic scope rules. A reference environment generally corresponding to a sequence of scopes. So scope is the lifetime for each variables, a lifetime, right? So and actually reference environment means like there's a sequence of scopes. So it's talking about all of the variables scope. Now we call it a reference environment. So reference environment also depend on what are called binding rules. Specifically, when the reference to a subroutine S is stored in a variable passed as a parameter to another subroutine, or returned as a function value. Okay, we call this a reference environment. And we have deep binding and shallow binding. So deep binding and shallow binding talking about how the variable being bind. Okay, it is a local variable or too deep, 2 level down or 3 level down. How deeply the memory you can find your memory. That's called deep binding and slope. Slope. I mean the shallow binding. And scope rule, static scope rule. A scope is defined in terms of physical structure of the program. We call it static scope. So most of the current language are compile-based language are static scope. So the scope of a variable is determined by where your variable is placed. That is scope binding. I'm sorry, that's static scope. And dynamic scope means the scope of the variable depends on when the scope is determined. So here we have a static variable in C. So here, if inside a C function, we put a static short integer. That integer n will be a functional level static variable. So whenever we call the same function, this static variable will be the same, referred to as same variable. This we call a static variable in C function. Scope rule number 2, nested scope. So the first part 1, we talk about the compile time scoping. Okay, here we talk about nested scope. So classical example of the static scope is the most closely nested rule. So an identifier is known in a scope in which it is declared and in a enclosed scope. So here if we have this one is some script, okay? So green color is a scope level. So we have local C equals 3, D equals 4, okay? And if we have a function in red definition, we have B definition. So when we print C and D, it's talking about the local variable that's inside your red level. So it will be printing now. The local, this local C actually is defined in green only, is local. So that when you do the red level, you cannot see it. So it actually will print out a nil over there. But D is determined as a variable that's not local. So basically, even though it's defined in green, but actually it is also available for the red one. Okay. So nested scope. Right here, it tells you that when you have the different procedure level, okay, and some variable S1, you will have a scope lifetime from here to here and from here to here. So basically, if it is inside its own function body, the function will be the same, unless that if calling some function that actually override the variable, okay? So scope rule, we will see classes, a relative module, and we discuss it abstraction and object-oriented programming language. So here we have different scope rule. And this I will omit, okay? These actually are older languages. Access to non-local variable static link. Each frame pointing to the frame of the correct instance of the routine inside which it is declared. So in the absence of formal subroutine, correct means closest to the top of the stack. Okay, so each time it determines a non-local variable, actually it will be determined by the stack, okay? You actually will depends on which level it is. And it usually will access the level that's closer to the top of your stack, okay? And this in some language it's not like that, but in C it's something like that. Okay, so access to a non-local variable, you basically, if you are in the assembly level or instruction level, you have to calculate the frame pointer and then get the edges to access the memory. Okay, access to non-local variable. So here, actually, in the simplest way is to use a static link. Okay, and that actually will be able to access the non-local variable. So basically, you determine the scope based on which call frame it is. Okay, scope rule in block. Okay. Okay, here let's consider this one is a Argo-6 Pascal language. Okay. So we have a constant n equals 10, right? And we have a procedure, right? So this constant n is the n10s scope. But inside is a blue one, we determine a n equals 20 that we declare it, right? So this n equals 20, this n is different from the outside n. So inside the blue level, the n20 will be in power. Okay, but actually before we call the n equals 20, we have an n assigned to m. That would create a static semantic error. Okay, so there is some conflict between the n10 and n20. Okay, and how can we resolve it? So sometimes it's determined by the declaration order. Okay, so Pascal said that the second declaration of n covers all fours. Second declaration of n cover all fours. So the semantic analyzer in line 5, okay, it actually in the line 5 would be n is being used before its declaration. Okay, so that is a semantic error. So we know that it's an n, but this n actually has a semantic error because it's used before it is declared. So it won't refer to the n outside. Okay, so that's a static semantic error. So for Pascal language, it's like that. But for some other language, it may not be that way. Okay, so nowadays nobody will do this anymore. We all try, the programming compiler will all allow the location independent definition of the scope. So declaration order for something that other than Pascal language, usually it depends on the definition level. It doesn't depend on the order of the declaration anymore. So whole block scope in C#. C# refers to Pascal notion of whole block scope. So C# still has the same problem that the Pascal has. So declaration in order of the scheme. So scheme is another language. Okay, so let's do this one. Okay, so we let A binding with 1, right? That A binding is 2, and this binding A in power of this parenthesis level. So B is bind with A, and then at the end we return B. Okay, so this A bind A with 1, and this A bind with B, but this A in power. So here, the nested declaration of A and B doesn't take effect until the end of the declaration list. So when B is defined, the redefinition of A has not taken power. Okay, so this declaration doesn't take out power because of what? Because this A is still associated with that A. So basically this one defined, but it's not in power. So this A actually using the binding to here. So when you print out B, it actually is binding with A, and B will print out the value here, 1. Okay, that's the in schemes language, how it is determined. So declaration and definition. Recursive type and the subroutine introduce a problem for language that require name to be declared before they can be used. Okay. Okay, but that's some language like C, C++ language handle problem by distinguish between the declaration and the definition. So basically, C, C++ solve the problem by using what? Using the prototype, right? Using the prototype. But in C++ recent implementation for GCC or something, this no longer is a problem. The order of the declaration is no longer a problem. Okay, but in the old days, the prototype are needed. Okay, the prototype is needed. Hello? Still there?
Still here.
Yeah, I'm sorry. Like actually, I see a warning that internet is not stable. Okay, that's why I ask. So declaration and the definition in C. So C language here, okay, we have structure manager. We have structure employee, but structure employee use the structure manager both, right? So this both we actually what? We have, because we have a prototype over here. We have a prototype over here. So this manager actually have been declared only, but there is no definition, right? But manager actually being defined over here. But here in employee, because this prototype, so it actually knows what? It is a structure, right? It is a structure. And this one is a pointer to that structure. And this is okay. But if you don't have this early prototyping or declaration, it's not okay because this manager will be undefined. But this happened in C language, not happening in C++ language. Okay. And on the right-hand side, we have also a prototype, right? This one is a prototype, functional prototype, right? So we put a function name parameter over here, right? And right here in my list function, we call the list tail, but the body is over here, is later. And right here we have the prototype. So this guy actually know that we are calling a function called list tail. And it is coming later, and you will bind to it later. Okay, so that's the use of the prototype to avoid the compilation error, and this is useful in C language. And then we have nested block. Variable declared in nested block can be very useful, as for example like C language. So basically, we can have the brackets, curly brace. And this make it a definition label. So this 10 value only valid inside this curly brace pair. Outside, if there is another 10, it mentioned to different variable. It is a different variable from this one determined or declared over here. So number 4, we have module class dynamic scoping. So module, to achieve information hiding, we make sure that some variable is only valid inside some module. The good thing about it is that if we have some module, basically when we integrate a larger program written by different people, usually you don't have the variable name conflict. But if you actually don't have that feature, and you call everybody and everybody can share the same namespace, then there are a lot of variable name that would be the same. For example, I declare some X, you also declare some X. Two may mean different things, but when our program integrate together, they may be problem, right? So if you have the idea of module and you actually do declaration inside the module, we call it information hiding. And the definition will not go out of the module, and you will not create a name conflict. Okay, so that's called modularization or information hiding. And we can also use encapsulation to use the private and public visibility specifier, so we can limit the where people can see and reduce the conflict as well. So module is some sort of abstraction. Module somewhat like class, but it actually is the older term. So module actually usually means a collection of subroutines, variables, or types. Okay, and objects inside are visible to each other, but objects inside are not visible from outside, and objects outside are not visible to the inside unless explicitly imported. Okay. And the namespace. Namespace, this word namespace is the module in C++ language. So when you talk about the namespace in C++ language, it actually means, this one actually means module. So it's some sort of abstraction mechanism. So you can declare some variable inside here. We have a schema 1, you have object 1, item 1, something, okay, schema 2, something like that. So namespace is a global compartment. Compartment means confined. You can actually use that to avoid naming conflict, okay? As I said, module can avoid naming conflict, especially when you integrate two module code from two different people. Naming conflict and collision always occurs and may occur, okay? When same program is using more than one library, especially a library written by different people with some variable or function having the same name, is very likely. The name collision may occur for global variable, global function, and classes. Default namespace is global namespace. So C language, we have global namespace. That's the default namespace. That's here. That's global environment. C language, we have default global environment. And some of the namespace is smaller. That actually is. So your global scope like this, and your namespace states may be smaller, but you can write in some program inside the scope, okay? And you can refer to here, or refer to here, okay? So namespace is actually the same as module. And it's somewhat like a class, but still has some difference. Okay. So module as abstraction, in here we have a C++ language. So we declare a namespace. Okay, so namespace is a module. So everything declared inside here can only be seen inside here. Okay. So here we have, from outside we have number module namespace, right? And here we can, if we try to use the random integer function, here random integer generation function, we have to use the module name domain specifier that actually is the double colon. And we use that, then we can call the function. If we don't use it, we don't use the using operator inside the C++, we cannot use the random integer. Then we have to do what? If we still want to call the random integer, then we will have to do random. We have to do random underline module, and then colon random integer. We have to call something like this. Okay, so basically to refer some function inside a module, you have two ways. Either you use the using statement, or you don't use the you don't use the namespace, but you actually use the domain specifier to access the function available. Two ways to do it. Okay. Okay. So that is the using namespace. In some language like Java, you use import. In Python, you also use import, right? But import and from some module import something, it actually means different thing. In Python, if you use the from something import something, it actually means the merging of the namespace. Okay, so if you say from import from module A, you say from module A import star, right? So whatever defined in module A, you don't need to use a domain specifier, right? But if you do import A, well, it is imported, but you still need to do A dot something to access some variable inside or function inside the module. Okay, so from something import some star or import something some module, it actually means different things. One is the merging of the namespace, the other one doesn't merge. Okay, the other one doesn't merge. But be careful when you do from something imports star, it merge the namespace. So some global variable may collide to each other. So use that. It is convenient to use it, but actually it is really dangerous. So here we can use module as a manager. So we have namespace random manager. There are two constants and they are a structure. It work like object. Okay, so it work like the object type, and they are methods. And these methods just like your constructor member functions, but they functionally like that, but actually they don't have the name called a class. And C++ has this module as managers, but it is different from the object as well. So C++ had two different versions of operating the module. One is using the object-oriented programming style. The other one is using this one called namespace, and it is the module style. Okay, but you can study it. Okay, and module type and classes. So on the left-hand side, we have this one is module types. Okay, on the left-hand side is the module type. Right-hand side is object-oriented type. So as you can see, object-oriented type, when we write a random number generator, right-hand side much easier than the left-hand side. But both will achieve similar features. Dynamic scoping. In a language with dynamic scoping, the binding of the name and object depends on the flow of the control at runtime. Okay, so the data actually bind to which variable, it depends on the runtime, not depend on the compile time. And which language is dynamic scoping? The Python is dynamic scoping. So here we have the example in figure 3.1, right? We have a global integer n, a procedure first that actually define n, and then there's a procedure 2 that actually call first, okay? So if we run the program from here, n1 equals 2, if read integer greater than 0, we run second, okay? So, but let's assume that, let me see, it is not actually, so initially we have n equals 2, right? And let's assume that we don't call the read integer, okay? Then we run first. And we go to first, we assign n equals 1, right? And then when we get out, suppose when we write integer, if this one is a local variable, we actually should get global, we should print out integer to be 2. So this n binding is what? Static, you bind to n equals 2. And that n actually belongs to procedure 1. It's local, so we don't care about it. Then this one actually will print out 2. But if it is dynamic scoping, you assign n equal 2, but you call first, and then n equals 1 have been defined. And then when you get out, the n equals 1 still invalid if it is dynamic scoping. So here you need to be careful about this. And some languages using dynamic scoping. So runtime error, sometimes you will bump into error. So here I Don't talk about it. Okay, the next one is the meaning of the name within the scope. So here we have a name. Name is the identifier. It's a mnemonic character string. Okay, so we have a name, right? And then we have pointer. Pointer is the address to the object. Okay, so name is the ID to the object. And then we have reference. Reference can be a pointer pointing to an object. So you assign the address to the pointer. Okay, and these different things actually we have the name, we have the binding, we have a reference environment, we have the scope of a binding. This we already defined it, okay? And we have the built-in time, built-in variable that's a language design time, global variable that's a programming time, loading time will be enclosed variable, and we have local variable that's a coding time. So different time for binding, and here are the terms for name binding and reference environment and scope of binding. So meaning of the name within the scope. Okay, if two or more names refer to the same object, we call them alias. What's that? So here we have a reference. If we have a reference, if two names associate with one object, we call these two names as aliases. Okay, indirect access is called pointer. Okay, so a name can refer to more than one object. Then that's called overloading. So a function refers to two different functions object with different parameter. We call it overloading. Okay, redefinition of a same name, say same maxima function in different class, we call it overriding. So overloading means a same name refer to two different objects. We call it overloading. Overriding means a name actually being redefined. That's overriding. Okay, overloading is related to more general subject of polymorphism, which allows subroutine and other program fragment to behave in different way depending on the type of its argument. So alias, what is alias? Alias is like, here we have a double, right? And then here we have this one, double sign, right? So this one, I call it alias. You create alias X. So from here, whatever X will be representing the sum. So sum actually associated with some memory. So when you pass it, it doesn't pass the value, it passes the address to it. So now X is also pointing to here, inside the function. Okay, so here your X actually what? You have sum, right? Sum increased by the X variable. Right, so say here if we actually call, let me see, this X actually is the sum, it's actually pointing to the same sum. So actually this one means the new sum equals sum times sum. So new sum should be sum square. So each time is sum square. And then here sum square equals X plus sum square. I'm sorry, this is plus 2 plus X, so it's become 2 sum. And here you plus 2 sum times 2 sum, so it becomes 2 sum square, it becomes 4 sum square. Okay, so that is the value being added. So basically the sum square equals the sum, it increased by 2 all sum square. Okay, quite complicated. Let me actually clean it out and write it again. Okay, so right here, initially you have alias to sum, so sum is available, and your X also pointing to here, right? It's created an alias for it. Then your sum increased by X, so actually sum increased by sum, so new sum will be 2 times the old sum. Sum will be 2 times the old sum. Then the next one, your sum square actually is plus equals sum times X times X, but now X is pointing to sum, so sum is the 2 times O sum. So actually this one is like 2 sums times 2 sums or 2 sums square. It becomes 4 O sums square. Okay, this new sum is 1 new sum square, but O sum should be 4 sum square. So it's somewhat a little bit complicated when you use this alias. Okay, so right here we have A, B, P pointer and Q pointer. So A assigned with the body of P. So body of P is a pointer. So P's body copy to A. Okay, and then 3 copy to Q's body. Q is a pointer, so Q's body. So 3 being assigned to here, and then P's body copy to P. Okay, so first one we copy the body of P to A. Second one, we assign 3 to Q's body. And then we copy the P's body value to B. Okay, that's how we use the pointers. Overloading. Some overloading happens in almost every language. We have integer versus real variable, and read and write in Pascal, function return in Pascal. Okay, these are okay. Overloading, I think, is not that hard. Okay, so here let's look at an example. We have known function. Okay, taking known. Known is the absolute value, right? So known function, you actually have integer, right? So when a greater than 0, we return a. If it less than equal 0, we return minus a. So that's the absolute value of a. Complex number has its own implementation. Okay, so a function named norm will be overloaded with two different flavors. That's the what? One reference name or ID refer to two different objects. We call it overloading. Okay, same name, different parameter list. That's overloading. And if the same name, same parameter defined in different class or different module, we call it overriding. Okay, generic function has a syntactic template, so that at the compile time you can assign the variable type or the replacement of some variable at the compile time. So macro in C++ is a generic function programming. And built-in function template in C++ and C-CRU and Ada. Okay. Overloading of the enumeration constant in Ada. This one I'll omit. Okay, Ada is not as popular. Okay, overloading of built-in operators. So here we have compress class, right? So it is one of the many exciting features of C++. It's an important technique that has enhanced the power of extensibility of C++. So that's operator overloading. So basically, you can overload the plus sign. Say originally the plus sign is to sum up two integer or double, but you can actually redefine the operator plus for the complex type you define by yourself. That's called overloading of the operators, and you just use operator plus as the function's definition. Okay, the next one is the reference environment. Reference environment, we talk about the whole variable name, binding, scope. The whole thing is called reference environment, and we have static scope and dynamic scope that we talked about it already. So we have deep and shallow binding that depends on which level you bind things to. Okay, this one we will omit. It's already out of date. It's an old-time example. So subroutine closure. If your language lets you store subroutine as a variable, so basically when you pass the subroutine as a function in JavaScript or in Python, it is okay to do it. Okay, let's do this one. Okay, that's called function closure. Basically, you can define A equals function, right? And then you define X, right? And then right here, you say document dot write, right? And here you do X plus brackets BR, right? So that's a definition of a function, right? And then we do B equals A, right? So B assigned to there, and then we do B of phi. So we print out a phi. Okay, so this one actually is what? This is a function closure. So function definition is right here, right? E assigned to A, right? So A is a variable, and A assigned to B, and we call B. Okay, this is called functional closure. Is that okay for this one?
That is fine.
Yeah, okay. So that's how we use it, okay? So the question about this is that we can actually put say we can have for example, we can have an array, right? Say here, if we have an array called f function array, right? And we put in f0, f1, f2, f3, right? And each of them you can do, say, g function, k function, h function, and g function, whatever. And then you can do f0 to execute some function. And then you change the index, you can apply a different function to it. Okay, that's a function closure. You can use that. It's a very convenient way of doing things. And also, this is okay for JavaScript and also okay in Python, okay? I try to avoid some useless old languages, but I try to emphasize something actually newer, more useful, because the textbook was written maybe 20 years ago. So some of the material actually, I couldn't say it is not important, but actually it's out of date, not really useful. So that's subroutine closure. So here we have subroutine closure, and then let's trace this one a little bit, okay? Here we have defined AP. This one is actually a Python example. It's called deep binding of the Python, okay? So a closure in a language is a static scoping capturing, okay? But it has the static scoping, but actually what? Deep binding, okay? Deep binding. So here we have definition of A function, C function, right? And then we actually call A function with the integer 1 and program C. So C as a function being passed C being passed as a what? As a parameter. Okay, so C doing nothing is a pass. So basically right here we run 1 and C, right? So 1 being passed and C being passed, right? So actually it actually passed this, and then C being passed to P. So P actually is where? Here the P actually is replaced by C function, okay? So number 1 is being passed to here, right? And here is an internal function. So actually we redefine B function as this, right? So it's a B function will print 1 because we call A1 C. So we first call A1C, right? Over here we call A1C. So actually the 1 being passed in is 1, right? And then the main function, if I greater than 1, right? No, it's not. So we run P function, but P function is actually running C function. Okay? If we are doing a deep binding, and then actually what? We call in C function, right? That actually is when we pass 1 and C. Okay. So here, if P function will print now 1, okay? And if here we have shadow binding, we have shadow binding actually this I, we pass 1, 2 here, right? 1, C here. And then we run this portion. and I is not greater than 1, so we call A2. So 2 being passed to here, and it is the B function. So when we call B function, we call A2, right? So basically, we have A1C, and then we go into here. So 1 actually not greater, 1 not greater than C, so we call A2B. So we call A2B, and then A2B come to here, A2 greater than 1, so we call P. P actually at this time is calling B, so B actually calling this function, right? Calling that function, but here if we do shallow binding, it will get 2. If we do deep binding, we will get 1, right? So that's the dilemma here, okay? So basically, the variable I can bind to 1 or 2, okay, depending on which way we bind. Okay, anyway, the key point is the Python language is using deep binding, okay? The conclusion here I wrote it for you is for Python language is called deep binding, okay? It's complicated, but you remember it's deep binding, so when we have stack like this, it binds lower portion, not the one is closer to your function call. It's called deep binding. So we call A1C here, it actually defines I equals 1, so it will print out 1 when you call A2B. The 2 is passed over, right? But the B function, when B function being defined, it actually binds with print of 1, okay? It's not happening when you actually pass the parameter 2 and B in to redefine it. No, it actually is the deep binding, okay, when we actually using the so-called Python language. And it's static scoping, but dynamic, but deep binding, okay? It's actually somewhat complicated. But to sometimes if you don't, so sometimes you run Python, you may feel like, okay, how comes the variable become like this? Because its binding way is quite different. It's dynamic binding, but it's deep binding, okay? Binding of the reference environment to lambda closure. First class variable and unlimited event. Okay, that's here something important is you need to know about first class value, second class value, and third class value. Okay, you need to remember the definition. First class status, if it can be passed as parameter, return subroutine, and then assign value to variable. This kind of value we call it first class value. If for first class value or first class function means you can do everything to it. Okay, you can do everything to it is a first class value. If you can only do pass it as parameter and then but you cannot returning those assigned to a variable, it's called second class value. And then third class value, you cannot even pass it. You can use it as only a value to be printed. That's called label. That's called label. So actually, you cannot do much about it. So third class value cannot be called or a set value from subroutine node or assigned to some variable node. It only can be a label. Okay, so that's the first class value, second class value, and third class value. Okay, here has a so-called lambda expression. Okay, and it's so-called the what's that? This one's called scheme language. Okay, so scheme language we define plus x lambda x this right. This is the definition of function. So here we have a lambda expression, not f with these two values. So basically, this one is expanded to f become this lambda 2 lambda y plus 2x, okay? And then if we have the f3, so f3 will evaluate as lambda 3 and plus 2y, okay? That's the f3. So first one, we bind f with plus 2, okay? So f binding with plus 2. And here, we actually binding the f with 3. So plus function binding with 3. So basically, you define lambda plus x, lambda y plus xy. Okay, so basically, this whole thing, eventually you will return 5. Okay, it based on 2 rules. First one, you bind in f with a plus 2. So basically, what f function is binding plus x function with lambda 2, and the lambda 2 here would evaluate the f function as lambda 2 lambda y plus x. Okay, it's a lambda y plus x, and plus x is lambda x lambda y plus x. So basically, you have lambda x plus y. So f become lambda 2 lambda y plus x. So if you have an f3, f binding with 3, it will be lambda 3 plus 2y. Okay, that's the function it is. And y assigned with 3. Y assigned with 3, x assigned with 2. And then eventually, you have plus 3 and 2, you will return 5. Okay, it's a little bit complicated. And the same function closure you can use Java to implement. So there's an interface functions called call function. So this one actually is the same as the lambda function we see over here in Scheme. So let's look at Java. It's a little bit more easier to understand. So we have an interface function. This one is the object. I'm sorry, a reference. Reference interface reference f. Okay, and you new plus x. So plus x is a class that implement interface function. So here you have plus x2. So the n assigned to 2. So actually plus x is a function called x equal 2. Okay, then you have this f function, and actually you actually call 3. Call 3 means the I is 3, and then f function defined is an interface function defined as what? Plus x is this constructor. So x being assigned with 3. So x is 3, and then you actually I'm sorry, x is assigned 2 because here x is 2, and you call 3. 3I is 3, so 3 plus 2 is print out 5. Okay. That's the object closure. Right hand side is the C double plus. Same thing. You assign the F2. So 2 is a parameter you pass to the plus class. Okay. So the constant x is now 2. And actually you will create a plus x and pass the value 2 to x. Okay. So x become 2 here, and then you actually call parentheses. So basically operator parentheses. So your f function would pass I equals 3 over there, and then you sum up with 5 and print out 5. Okay. So this actually, and here we have C# similarly, and I will omit it. It actually take a while to explain. And lambda expression happen on C#, happen on Ruby, happen on different language, OCaml, okay, and it actually doing similar things. And lambda expression in C++ 11, okay. And this I don't spend too much time. It actually take a while to explain it, okay. You can download and study it. Okay, let me see how much time we have. Okay, we almost run out of 2 hours. So let me see if here anything important we need to mention. So lambda expression is the substitution of the function. Let me see. We have this compile process, should be easy. Separate compilation should be okay. Macro. Macro is another way you can expand your code in C++. And macro basically is a substitute of the context, okay? It's only a substitute of the context. So this one, you can study it. Okay, I actually would just make a conclusion for this chapter. This compilation. Okay, so basically, in this chapter, we talk about a few data type and memory model for the languages. So the language feature can be surprising subtle. It's very complicated. But to understand each language, you have to learn its memory model first. Okay, and it actually, where memory model means the binding of the values and when it is available, when it's not available, and when it will make change, when it will not make change. So that is the combination of the reference environment, name, and binding and scope. Okay, so here in this chapter, we try to summarize to talk about these different things. And in terms of the more detailed stuff like lambda expression, I actually don't have time to actually go through it completely. So you should spend time to study it from the textbook. Okay, a language that is easy to compile usually lead to better languages. So I try to avoid those complicated things because most of the programmer doesn't know how to use it. If some feature is like that, actually it's eventually useless. Okay, a language easy to compile, easy to run, will end up with better code, fewer compiler error, and also smaller, cheaper, and faster compiler, better diagnostic. That's what we actually want to promote. So Python, JavaScript, all has these different features, and it's more portable right now. And then C++, Java still stay in desktop applications. Okay, that's about it for today. Any question?
No questions.
So I try to present the whole view, okay? Today I try to present the whole view about the environment and the variable definition and binding and scoping, okay? And I try to avoid those technical details because at the end, we want to have a language that's easy to compile, easy to write program, fast to run, fewer bugs, cheaper, right? If a language tend to be too complicated, you need to remember 3,000 different syntax rules that eventually those languages will be obsolete, right? Because it's not easy for people to use it, okay? So that's it. Thank you. That's it for today. Bye now.
Thank you.
Bye-bye.